Today we're going to talk about something called value objects, also known as VOs. Before we jump into the theory and formal definitions and stuff, let's start with an example, because it will be much easier to understand where and when value objects make sense. Today's example is about calculating shipping costs. Typically, to calculate the cost to ship a package depends on few factors and variables. It can include things like package dimensions, weight, the distance between the origin and the destination, the carrier, the speed, how fast you want the package to be delivered, value of the package, and so on. We're going to assume some of the things related to shipping calculation in this lesson, and we're going to use a very simple calculation to not go out of the scope. So please, don't quote me on the actual numbers or the formulas. They are irrelevant and don't really matter for the topic of this video. So we're going to focus on just a couple of factors of shipping cost calculation, which are the package dimensions and the weight. We use these to calculate something called a billable weight. Billable weight is something used by carriers to calculate the shipping cost per package. Billable weight is based on something called the dimensional weight, also known as the dim weight, and the actual weight of the package. The billable weight will be equal to the one that is greater between the dim weight and the actual weight. So if the dim weight is greater than the actual weight of the package, then the dim weight will be the billable weight. Otherwise, the actual weight of the package will be the billable weight. Let's open the code here. And I've created this billable weight calculator service class behind the scenes, which contains a single method called calculate. This is going to be the class that will calculate the billable weight for us. So as you can see, the method accepts width, height, length, weight, and something called dim divisor, which we'll talk about in a minute, and it should return the proper billable weight. The types, as you can see for now, are set to integers. It could be floats or strings, but to keep things simple, I decided to use integers for this example. Also, the units for the given dimensions are assumed to be in inches, and the units for the weights are assumed to be in pounds. As I mentioned before, the billable weight is either the dimensional weight or the actual weight, whichever is higher. So we'll create a new variable here called dim weight, and let's set that to 0 for now, and then we can simply return the maximum value between the actual weight and the dim weight. The dimensional weight uses the length, width, and height of the package, and the formula is basically the product of the width, height, and length divided by some dim divisor. Dim divisor is a number that is set by a specific carrier, so FedEx may have a different dim divisor than USPS, and so on. We're going to just round the final result to the nearest integer, and then cast to int to return it because our return type is set to int. Let's test this out quick to make sure that it works. I have created a shipping calculator example PHP file behind the scenes as well, which we'll use as a playground to run the code in terminal and test things out. So we have a package variable, which is an array for now, and contains the weight and dimensions. Then we have the dim divisor set to 139, which is the value for the FedEx carrier, and then we are simply instantiating the billing weight calculator service and calling the calculate method to calculate the billable weight. So let's open the terminal and run this code. And sure enough, it works, and it prints 7 pounds. If we were to set the actual weight to something like 8 pounds, for example, and we run the code again, we see that now we get 8 pounds printed on the screen, because the actual weight is now higher than the dim weight, and therefore it returns the actual weight. So what's the issue here? Why can't we just use this service class the way we are using now? Why can't we just pass these values the way we are passing and calculate the billable weight? In some cases, this code is perfectly fine and it would work. However, in some cases it would fail. What if we pass negative values, or what if we pass 0 for the dim divisor? Let's try it out. Let's say that, for whatever reason, the width was set to -9. If we run the code, we see that it returns 6 instead of 7. That's because when the width, length, and height are multiplied, the product of that becomes negative number, and therefore the dim weight becomes the negative number, and the maximum between the negative number and 6 is 6, and therefore 6 gets returned. Let's try out when we pass 0 as the dim divisor. Let's run the code and we get division by 0 error. So as you can see, a lot of things can go wrong here, and we don't really have any kind of validation. What if we also wanted to have some kind of maximum allowed package dimensions, and we didn't want to allow some large numbers like this? One way to fix this is, of course, to have some kind of validation. We can either have this validation outside of the service class, or we can have it within the service class, within the calculate method. So let's revert this back to the proper values. Let's go into the calculate method and let's add some validations here. We're going to use the match expression here to avoid having a bunch of if-else blocks. So we'll do something like with less than or equal to 0 or with greater than some maximum value. And we'll just hard code this to 80 for now. If one of these passes, then we'll simply throw new invalid argument exception with message invalid package width. Let's do the same thing for the height. Let's do the same for length, and let's update the wording here. And then we'll do the same for weight. And finally, we'll do the check for a dim divisor, where dim divisor should be greater than 0. Let's add some default case, and default will simply return true. We can even assign these to a variable, but we don't really need to do that because we don't need to keep the value whether it's true or not. We're just simply throwing an exception if one of these values are invalid. So let's test this out. We'll go back to the shipping calculator example, and we'll simply pass a negative width. Let's run the code, and sure enough, we get invalid package width. Let's set length to 0, run the code, and we get invalid package length. Let's set height to negative number, and we get invalid package height. Let's set weight to something like 500, which would be higher than the maximum value, and we get invalid package weight. If we set the dim divisor to 0, we'll get the invalid dim divisor exception. So the validation is working as expected. Now what about the units? I mentioned that we assume units for dimensions were in inches and the weights were in pounds. But what if we wanted to use metric units instead of the imperial ones like grams, kilograms, and meters? One way to solve that would be to accept the units as other arguments in this method, or we could simply accept an array that would contain the dimensions, the weight, their units, and so on. Which could work and would be fine in some cases, but it would fall apart as things would get a bit more complex and as requirements would change. So as you can see, these arguments are no longer just simple scalar values anymore. There are more things to it. There is some validation involved, there could be some units involved, there might be some formatting involved, where we might want to format these in certain ways, and so on. So it's not just simple scalar integer values, it's just more information is needed for these arguments. So when there is need for such additional information, and the simple scalar type is no longer enough, or when you need to group multiple arguments into a single type, then that's where value objects could be a better alternative. So what is a value object? A value object based on formal definition is a small object that represents a simple entity whose equality is not based on identity. For example, two value objects are equal when they have the same value, not necessarily being the same object. The keywords here are equality, entity, and identity. As you remember, we covered entities earlier in this series, and while value objects may sound or seem similar to entities, there is one major difference. Entities are typically identified by something like an ID, while value objects' properties are its identity. So value objects don't really have a specific identifier. Entities generally have a life cycle. For example, if we had a package as an entity, its properties could change. Like package can have the dimensions like width, length, and height, and can have weight as its properties, and those properties could change relative to that specific package. But the package identity would remain the same. We can compare two packages for equality by checking their identifiers, like IDs, to see if it's the same package or not. Because we could have two packages that have the same dimensions and weight, but they are still not the same package. But if two dimensions have the same width, height, and length, they are still the same dimension objects, regardless of which packages they are used for. This type of objects, where the equality is based on its property values, are called value objects. Value objects usually represent something quantifiable, measurable, or they describe something. For example, amount, weight, address, email, phone number, dimensions, or even age could be modeled as value objects. So let's go back to our example, And let's see how we can model our arguments as value objects. There are a couple of options here. We could either create value objects for each individual argument. So we could have something like width, value object, height, and length. Or we could simply group these three arguments into a single value object called dimensions. So in this example, instead of representing them as separate value objects, I'm going to combine them into a single value object called package dimension. So let's create this value object. And within the constructor, we're going to accept the scalar width, height, and length values. Value objects have few characteristics. One of them is that they must be immutable. So the first thing that we need to do is that we need to turn these into properties. So we'll do public, and to make this immutable, we'll make these properties read-only. Now, the reason the value objects need to be immutable is to allow sharing value objects safely. It solves something called aliasing box, where if the same package dimension object is passed around in multiple places, and one of them update its width, for example, that would also affect other places where the package dimension object is used. If this sounds a bit strange or need a refresher, I recommend watching the lesson in second section about how variables and objects are stored, where we cover this in detail. In addition to immutability, another characteristic of value objects is that it should be valid by default. Value objects are usually assumed to always be in a valid state. This means that we can move validation related to package dimensions from the service class into this value object class constructor. Now, of course, instead of having these hard-coded, we could have them be part of an enum class or maybe a constant or something like that. But for now, I'm just going to keep them hard-coded just for the simplicity of this example. Value objects should also be side effect free. Let's say that we wanted to have a method that increases the dimensions. Maybe a method that would increase width of the package for whatever reason. Typically, you would add a method within this class called something like increment width or increase width, which will accept the number of inches to increment the width by, and then you would do something like this, width plus equals width. Now, thanks to read-only properties, we're not able to do this because the package dimension value object is immutable, meaning that we cannot modify the property. If we didn't have the read-only properties and these were private properties, there would be one way to achieve immutability prior to PHP 8. However, something like this would break that immutability because this would modify the internal state and cause some side effects, and therefore it should not be allowed. This is why read-only is such a great feature of PHP 8. Now, to still be able to support such a method on a value object and be able to increase the width, instead of trying to modify the internal state, we can simply return a new package dimension object. So we can do new self and simply pass the updated width as the width argument, and all the other arguments would be the same. So this does not cause any side effects, and it does not interfere with mutability because it does not modify the internal state. It simply creates the new object or the new instance with the updated value. Also, we mentioned units. We could accept another argument here called unit and make it a value object as well, or make it an enum class. But we're not going to do that for now to not make this video too long. For now, we're going to assume that the conversion to inches happens somewhere else outside of this class. And this class and this method always expect the dimensions to be in inches. Now let's talk about the equality and how value objects get compared. As you know, to compare two objects in PHP, we could either use double equal sign or triple equal sign. Double equal sign compares two objects by comparing its property values using double equal sign as well. And the triple equal sign, also known as identity operator, compares object references. Now, double equal comparison sounds like a good way to compare value objects because, as we said, value objects are compared by their values. The problem is that double equal sign would compare its properties also using the same strategy, the same double equal sign comparison, and not the strict comparison. I like to always use strict comparisons and strict types. So instead of using double equal sign to compare two value objects, we're going to have custom equality check methods within our value objects. So we're going to add equal to method here. So we'll do public function equal to, and this will accept other package dimension, and we'll simply compare every single property of the current package dimension with the other package dimension using the strict comparison or the identity operator. So we're good with this value object. Now let's adjust our service class here. So we'll simply access the width, height, and length from the value object, and then we can do the same thing for the weight. Because weight can also be a value object, it can also contain units, and it also has the validation and so on. So instead of accepting int, we can accept weight as its own value object. So we'll create this value object here, and within the constructor, we'll accept the scalar weight value, which is going to be in pounds, and we're going to assume the units for this example as well. And we'll copy this check, and here we can just use if conditional instead of a match expression. Next, we're going to add the equal to method here as well. Now, to make sure that we have the equal method to all value objects, we could introduce an interface, something like a value object interface or something like that, and implement it in all the value objects, which would define equal to method as a requirement. But we'll skip that for now. Let's go back here, and let's remove this from here, and let's adjust this as well. And to not have the weight as a redundant property here, we can just call this value and replace these to value. That way it reads better where the variable is called weight and the property called value instead of having weight. Now there's this dim divisor that we need to figure out what to do with. Should we put this into a value object? Or maybe we should keep it the way it is. I don't want to use value objects for every single thing if it's not needed. We can extract this into an enum class because the dim divisor is kind of a static value, right? If we turn this into an enum class, then we don't really need to validate because we can simply type hint this to be dim divisor, and then the given case would already be a valid case of the enum class. So let's get rid of this from here, and let's create the enum class. It's going to be a backed enum, and we'll create a case for FedEx and set it to 139. And then we'll adjust our service class and access the value this way. So as you can see, our calculate method now looks a lot simpler, more readable, and less prone to bugs. You don't have to turn everything into value objects. Reach for value objects for when it actually makes sense. See if there is more to that argument than just its simple scalar value or the scalar type. Also, don't create value objects only because you want to have each object validated in its own constructor. It's just that sometimes value objects make more sense. Value objects are usually used and are part of the DDD, or the domain-driven design, though it can also be used in other architectures, and I've used value objects outside of DDD. Now let's test this out to make sure that it still works. We need to adjust the code in the shipping calculator example PHP file. So we're simply going to create a variable called package dimensions and create a new package dimension value object. And we're going to take this and pass that into this value object. Let's import that, format the code, and this looks good enough. We'll copy this and pass it into the calculate method. For the weight, we're simply going to create a new weight value object and pass that in. And for the FedEx dim divisor, we'll do dim divisor FedEx. That way we can get rid of this as well. Let's open the terminal, clear this out, run the code, and as you can see, everything is still working. We can change the actual package weight to 9. Let's run the code. And now, because the package weight is higher than the dim weight, it's using the package weight. We can set this to 0, run the code. The validation works, but the validation now is coming from the weight value object. Now let's say that we wanted to calculate the billable weight of the same package if it were 10 inches wider. So we could call increase with method on the package dimensions and pass 10 as the 10 inches. Let's assign this to a variable called wider package dimensions, and then we'll simply calculate the wider package billable weight using the same method, but we'll pass in the wider package dimensions here, and we could share the weight, and we could also move this to billable weight service, and we can echo the wider package billable weight as well as the regular billable weight. Now, before we run this, let's change the original package weight back to 6, and let's open the terminal, clear this out, run the code, and initially it returns 7 pounds, which is correct, and the wider package billable weight is 14 pounds. because we've increased the width by 10. So if you pull out a calculator and plug these numbers in, you will get 14 when rounded. Now notice that the original billable weight is unchanged. That is because of immutability and the side effect free value objects. Calling increase width here does not change the width of the original package dimensions. Instead, it creates a new package dimensions object. If it were not immutable, what this would do is that it would actually change the width of this package dimensions to 10, and both of them would print 14. All right, so I think that's enough with this example. Let's now talk about the differences between the entities, DTOs, and value objects. We've already established the differences between the value objects and entities. We know that entities are identifiable by an ID, while value objects don't have such identifiers. Their properties are its identity. Unlike entities, value objects are also immutable and are side effect free. The difference between the DTO and the value object is that DTO is just a data transfer object. It's a dummy object whose only purpose is to transfer data from one place to another, and is focused on just the plain data. It does not have any behavior or logic. The value objects, on the other hand, can have some logic and behaviors, including the validation. To help further understand what value objects are, we can break the concept down into 4 principles. They measure, quantify, or describe something in your domain. They are immutable. They maintain referential identity, but lack their own identity, and they provide side effects-free functions. Let's take a look at the first principle. It measures, quantifies, or describes something in your domain. Oftentimes, when you're trying to measure or quantify something within your domain, you'll find that there is this common relationship of some measurement with a particular unit or scale. When you come across scenarios like these in your domain, they present great opportunities to use value objects to model them. Probably the best real-world example of value objects is money. The simplest scenario to think about is your own personal bank account balance, which tracks 2 important things. The first and most obvious is the amount of money you have. But the second, and perhaps less obvious, is the currency that money is stored in. As we all know, not all currencies have the same value, so it's important to establish that relationship to correctly represent a bank account balance. Another good example is temperature. When we measure temperature, there are 2 required bits of information needed. The first is the total number of degrees, and the second is the scale used. We can describe this relationship by creating a temperature value object and encapsulate these 2 properties within that class to represent a measurement of temperature. The last example we'll look at is color. One way we could model color in our domain would be through the use of RGB values. By using these RGB values inside of a color value object, we can provide the calculation for new colors derived from those values. The second principle of value objects is that they are immutable. If we think about our bank account example, and suppose we have a balance of $1,000, we can't just suddenly change the currency and decide to have 1,000 euros. That just doesn't make sense because euros are currently worth more. The properties of value objects are related. They describe something. If you change one property, it completely changes the meaning of the object. This is why value objects are immutable. If you need to change a property of a value object, you need to destroy and recreate the entire object to ensure the integrity of the object remains intact. If we think about our temperature example again, we can't just change the scale of measurement without affecting the total number of degrees. This is why it's important to keep value objects immutable. 77 degrees Fahrenheit is obviously not the same as 77 degrees Celsius. If we want to move from Fahrenheit to Celsius, we would need to recreate the entire value object. This will maintain the relationship between the properties. The third principle of value objects is they maintain referential identity, but lack their own identity. To take a closer look at this principle, let's consider 2 different car objects and take a look at the paint that was used for each of them. While observing the car objects, we can see that the paint buckets used for each car were different, as indicated by the different paint bucket IDs. This is the identity of the paint bucket itself. However, even though the cars were painted using different paint buckets, we can still compare the 2 color value objects and determine that both cars are the same color. Even though they came from different paint buckets, the color is the same. This is referential identity. Let's look at another example. Say we want to determine if two different people have the same net worth. One way we could do this would be by looking at their bank account balances. Now, if we think about the amount of money each person owns in their bank account, each person will have a collection of uniquely serialized currency that only they possess. That's the identity of the currency itself, specific to each person. But we can evaluate the bank account value object and determine if they have the same net worth using referential identity. In this case, because the bank account value objects are different, we can make the determination that these individuals do not have the same net worth. The last principle of value objects is that they must contain side effect-free functions. If we stay with our bank account example and say we want to add a new withdrawal function to be able to take money out, and in addition, we also want to be able to perform logging each time that a withdrawal is performed, it might seem reasonable to put that logging inside of our newly created withdrawal function. However, the problem with that design is that it violates the principle of side effect-free functions. Each time we perform a withdrawal, that function will be creating a side effect of performing application logging. It has the potential to write to a log file or even a database. To keep your function side effect-free, remember to only be measuring or quantifying something within your value objects. Now let's recap the 4 principles of value objects again. The first is it measures, quantifies, or describes something within your domain. Remember to think about the relationships we established between properties inside of our value objects. If we think about our bank accounts, it's important to have both the total amount of money and the currency it's in. This is similar to how temperature works as well. You need to have both the total number of degrees and the scale used to take an accurate temperature. And lastly, think back to how we use the relationship between RGB values as the basis to create new colors. The second principle is they are immutable. Remember to think about the example of changing only the currency value of our bank accounts. You can't go from $1,000 to 1,000 euros. That just doesn't make sense. Each currency is valued differently. So when you need to make a change to a value object, remember to always destroy and recreate the entire object. The third principle is they maintain referential identity but lack their own identity. Think back to how we were able to determine that 2 cars were painted the same color, even though they came from 2 different paint buckets. The identity of the 2 paint buckets were different, but by looking at their color value objects and determining that their referential identity was the same, it allowed us to say that both cars were painted the same color, even though they were painted from 2 different paint buckets. The last principle is they must contain side effect-free functions. Remember when we tried to perform logging inside of our withdraw function? That logging had the potential to write to a file or even a database, creating a side effect within our function. When you're designing your value objects, make sure your functions only measure or quantify something.